The power of mathematics that makes the dream of living longer a reality. How long can we live? Just 100 years ago, living as long as people do today was difficult. In the early 1900s, the average life expectancy around the world was only about 31 years. Today, 100 years later, it has increased to about 73 years. In developed countries, the average life expectancy is over 80 years. As medicine advanced, researchers developed treatments for diseases that were once difficult to cure. Preventive medicine has also advanced, making it possible to predict the risk of disease before it develops. So how does mathematics help extend human life? To live a long and healthy life, avoiding disease is important. But even after a disease develops, effective medicine can save lives. That is why developing new drugs and vaccines is so important. However, creating a new medicine is much more complicated than it seems. First, researchers must identify the cause of the disease. Then, they must understand how that cause works inside the human body. So, is it possible to determine in advance exactly where a medicine will work inside the body? This is where mathematics comes in. We can represent the molecular structure of a drug with three-dimensional coordinates. We can also calculate the energy changes that occur when molecules interact. In this process, equations such as the Schrödinger equation and the Langevin equation are used. The Schrödinger equation describes the states of extremely small particles. It can also analyze how a drug molecule interacts with the substance that causes a disease. The Langevin equation describes how a particle moves as it collides with surrounding molecules in a fluid. It is like placing a small ball in water and watching it move around as it collides with water molecules. These mathematical calculations allow scientists to design molecular structures so that drugs work effectively at the intended target. Developing a new drug requires many experiments. Researchers must test its effectiveness and safety in animals. Will a drug that works in animals work the same way in humans? Will the same drug have the same effect on everyone who takes it? Mathematics also helps solve these kinds of problems. Scientists can use differential equations to build models of how drugs move and change inside the body. They can also run virtual experiments on a computer before conducting real ones. For example, people and laboratory animals have different lifestyles and biological rhythms. People are active during the day, so they are exposed to more light than nocturnal mice. Mathematical models can also compare how these differences affect the effectiveness of a drug. Then, could the day come when scientists reduce experiments on real animals and people and instead test new drugs first in a virtual environment on a computer? Rather than replacing real experiments, mathematics can serve as an important tool for predicting possible outcomes before experiments begin. There is something just as important as treating disease. It is finding disease accurately. Early detection makes it possible to begin the right treatment. So how can doctors see inside the body without opening it? This is where medical imaging technology comes in. X-rays can quickly detect fractures or lung diseases. However, X-ray images show the inside of the body as a two-dimensional image because different structures overlap. As a result, it can be difficult to determine exactly where inflammation or cancer cells are located. CT and MRI overcome these limitations. They take many cross-sectional images of the inside of the body and stack them together to create a three-dimensional image. It is like taking pictures of thin slices of bread one by one and then stacking them again to see the whole shape. CT contains some fascinating mathematics. First, X-rays pass through the body. The system then measures how much X-ray each part of the body absorbs. However, taking an image from only one direction cannot reveal the body's internal structure accurately. So X-rays pass through the body repeatedly from many different directions. Each measurement from one direction creates one equation with each part of the human body as an unknown. Measurements from many directions create many equations. Together, they form a system of equations. The computer solves this system of equations and calculates how much X-ray each part of the body absorbed. But this is not the end. The calculated numbers must be turned into images that we can see. In other words, the information expressed as numbers must be converted back into images. This process uses many mathematical methods, and the concepts of functions and inverse functions that we learn are also connected to this kind of mathematical thinking. We can detect diseases earlier and treat them with new medicines. Then, will humans one day be able to stay young forever? This is something we still cannot do. As we age, the cells in our body gradually grow old as well. As cells become damaged and lose their function, our body also slowly becomes weaker. If we could slow aging even a little, could we also extend our lifespan? The Gompertz function is used to study this phenomenon mathematically. The Gompertz function describes how the mortality rate increases with age. It can show on a graph how the mortality rate increases exponentially as people grow older. What would happen to the graph if we could slow the aging of cells? If we could slow the rate of aging, we could delay the point at which the mortality rate begins to rise rapidly. It is like delaying the departure time of a train, pushing the end of life a little farther into the future. Scientists are conducting a wide range of research to extend the lifespan of cells. They study ways to maintain the length of telomeres at the ends of chromosomes. They are also looking for better ways to repair cell damage. Researchers are also working to improve the function of mitochondria, which produce energy for cells. Extending life does not simply mean living longer. Increasing the years of healthy living is even more important. To make that goal a reality, life science, medicine, computer science, and mathematics are all working together. The equations and functions learned today may one day help treat diseases, extend human lifespan, and create healthier lives. How far will mathematics be able to extend the human lifespan in the future?